Whenever two objects have a property that we call mass, they will experience a force that we call the force because of gravity. So if we have two objects, let's say in deep space, those objects A and B here labeled, object A, just because it has mass, it would feel a force towards object B, so it will experience a force on A due to B. The other object B would also feel a force on the direction towards A because of A. Both forces, they would be opposite directions and equal magnitude. Now if both masses are very small, for example the size of a human, that force would be barely noticeable. So we only really feel that force when we're looking at things huge as planets or stars. Actually, the force because of gravity is the weakest of our four fundamental forces in the universe. So just like we did when we were discussing our electromagnetic fields, we may have figured out a concept of a gravitational field, and we can measure the gravitational field strength by dividing the force which is exerted by that object by the point mass, so the small task mass that we're using to analyze this field. Since force is a vector and mass is a scalar, the gravitational field strength will also be a vector pointing at the same direction as the force. There is a quite interesting particular case. We usually use letter G for the gravitational field strength, and we measure by force divided by mass. So it's force because of gravity over the mass of our test object. Now the funny thing is, if we are observing a force because of gravity at the surface, our force would be exactly the weight. And that's actually expected, isn't it? So at the surface we would have our acceleration of gravity to be exactly g, and that value would be our 9.807 that we used to, meters per second squared. That actually shows us that we may describe our gravitational field strength in two different units. Meters per second squared is fine, but also, if you remember, this is force and this is mass, we could also describe as newtons per kilogram. So when Newton was observing this phenomena, he observed that those forces, they were always attractive. So gravitational forces, they were always towards the objects. They were never repelling. Also, he noticed that the forces, they were proportional to 1 over r squared, so 1 over the distance squared. If you double the distance, the force would weaken by a factor 4. If you have half of your distance, then your force would be 4 times stronger. Also, he found out that this force would be proportional to both masses involved. So if I have twice, if I make one of the masses twice as large, then this force will be twice as large. If I make the other mass twice as large as well, then it would be 4 times the original force. So that could be basically described as F, our gravitational force, would be proportional to capital M, which would be the mass of, let's say, the largest object or one of the masses, lowercase m, which is the other mass, over r squared, which is our radius squared. And to equate that, a constant was designed to make that equal. And this is our universal gravitational constant, and you should have that in your physics booklet. The value is 6.67 times 10 to the negative 18 newtons meter squared per kilogram squared. And remember that this force is always attractive. So this distance is from the center of your masses. So if you have a very massive planet, you would have to take into account the radius of your planet as well, because the forces, they are not taking into account the radius of those planets themselves. So, a fairly straightforward question. Calculate the force of attraction between an apple of mass 100 grams and the Earth. This is the kind of problem that I told you that you should take into account the radius, right? So basically, if it's in the surface, the radius will be the distance between our two masses. So we would have a mass capital M and a mass lowercase m. This is my diagram, okay, my free body diagram, and the forces pointing towards each other, and they are going to be the same magnitude, opposite directions. So if I want to calculate the strength, so the actual, well, not the strength, but the actual magnitude of this vector, it would be capital M, G, that's our universal gravitational constant, capital M, lowercase m, over r squared. In this case, that's the radius of Earth, since the apple is in the surface. So, we're given the mass of the Earth, we're given the radius of the Earth, we should know this constant, so let's put the numbers in. So 6.67 times 10 to the power negative 11 times our large mass, which is 6 times 10 to the power of 24 kilograms. Everything is in SI units. This radius, I'll just write this as 10 to the power of 6, right, meters, because it's in mega. Anyway, our small mass here is 0.1 kilograms. All of this divided by our radius squared, which is 6.4 times 10 to the power of 6, and everything squared. That's the whole radius squared. Usually students sometimes forget to put the 10 to the power 6 squared as well. Don't. You're squaring the whole number. So this should give you a value of around 1.1 Newton. So another quick example. Calculate the force of attraction between a proton of mass 1.7 times 10 to the power of negative 27 kilograms and an electron of mass 9.1 times 10 to the negative 31 kilograms when they are at a distance of 1.5 times 10 to the power of negative 10 meters apart. So what we have here, well, we have a proton and an electron, and we know that there will be an electromagnetic force trying to bring them closer, right? Since one is negative, the other one's positive, there will be an electromagnetic force. However, we are now just looking at the gravitational force. So, and then we may compare. Just for fun, the electromagnetic force would be in the order of 10 to the power of negative 8 newtons. Alright, just so we have an idea. Now, let's calculate our gravitational attraction force here. So that's capital M, mass of one particle, mass of another particle, right, over the distance between them squared. Now, they're very tiny. The distance is much, much larger than the actual radii of both particles, so we can just neglect the radii here and just use the distance between them. So if we put the numbers in, that would give us, I would just put 6.67 instead because of our significant figures here. Since we only have two significant figures in each number, there's no point in using 6.67. So 6.7 times 10 to the negative 11 times, now we'll have to use both masses, so 1.7 times 10 to the negative 27 and 9.1 times 10 to the negative 31. All of this over r squared, which is 1.5 times 10 to the power negative 10 squared. Now, I'm not putting units since everything we know here is in kilograms, so all masses are in kilograms, all distances are in meters, so there's no point There's no need for it. If you want to put it, that's fine. But I know for sure that my force here will be newtons just because of the units that I'm using. And I'm saving time and just some space here, some room. If we work down those numbers, if you put in your calculator, you should find 4.6 times 10 to the negative 48 newtons. So if you compare those forces, I think you may reach some conclusion on how neglectable one of them is compared to the other one. So you can see that our gravitational force is, well, it's it's laughable compared to this one. Look, it's 10 to the power of negative 40, right? So that's 40 orders of magnitude away from this one. So it's unthinkable. This distance, this gap is unthinkable. So this is basically nothing compared to this force.